Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a roundup of the chain rule lecture in a differential calculus course. This is kind of the bucket of questions at the end that are more the high-level synthesis questions, and I like to separate these from the basic examples. So let's go ahead and see what I consider to be synthesis questions. Anybody who's watched this video series so far knows that I really like differential equations, and I would prefer my students to have a strong familiarity with dealing with just a basic idea of a differential equation prior to getting past Calculus 2. Because once you get past Calc 2, that's when you're likely to enter into differential equations, and having been pre-exposed to it, or to them I should say, is kind of important. So just like we've done in the past, we're handed a differential equation y double prime plus 2y prime plus y is equal to 0, and we're asked to find a solution. We want to find a function y whose second derivative, when added to twice its first derivative and then to the function itself, will turn off, basically. And the author of the problem tells us, by the way, the solution is likely of this form. So please find me what the coefficients a and b are. The best way to do this, as I've shown in previous videos, is to write y, 2y prime, and y double prime stacked like this because you want to add them up to become 0, and it's just easier to work this way. So let me write out y. Y is a e to the negative x plus b x e to the negative x. And then we'll take twice the derivative. Well, I'll write the 2 out front, and then I'll take the derivative. The derivative of a e to the negative x. This is probably the first time you're seeing this. This is actually a chain rule. This exponent is not x. If it was just e to the x, then I'd say the derivative is e raised to the x power, but it's not. So let's see what this is. Well, the constant hangs out. The derivative of e to a power is e to the power, but then you have to take the derivative of the power. Derivative of negative x is negative 1. So there you go. That's a good chain rule problem. Plus b, and this one I'm going to go ahead and write it this way, times x e to the negative x, we are going to take its derivative. Okay, let's go ahead and do that. I'm going to distribute the 2 through as well. So this becomes a negative 2a e to the negative x plus 2b. And now we're going to take the derivative of this product. The derivative of the first is 1 times e to the negative x. So 1 e to the negative x. And then the first, remember product rule, you're using summation. So plus the first times the derivative of e to the negative x. Well, let's again have a conversation about that. The derivative of e to a power is e to that power. But then you have to take the derivative of the power itself. And the power is negative x, so the derivative of a negative x is a negative 1. Let's go ahead and clean that up. Let's see, I get negative 2a. Actually, do I have room off to the right? I do. Let me write it off to the right. I have a negative 2a e to the negative x plus 2b. Again, e to the negative x. And then remember, this 2b is distributing through, so it's going to be minus 2b x e to the negative x. Now, I have to be honest with you, that's not cleaned up enough. There are like terms there. these two are alike. They have the same algebraic expression they're attached to, e to the negative x. So I'm going to group them up. I'm going to write this over here. So this is equal to, let's see, it'll be a quantity, negative 2a plus 2b e to the negative x, and then finally minus 2b x e to the negative x. Now, some people will say, can't you factor out an e to the negative x out of all that? And the answer is definitely yes, you could. In fact, that might be a great idea, so I don't mind doing that. If you want to do that, let's do it. Let's go ahead and factor that out. That means I don't need these parentheses. I could just write it like this. Okay? So again, I just basically factor out e to the negative x then. And now we're going to take the second derivative. So that was twice. Oh, shoot, that's going to be a little confusing. So let's go ahead and factor out a 2. So let me just say that's why our first derivative is not what we just arrived at. That's actually twice the first derivative. So the first derivative is actually a negative a plus b minus bx, and that is e to the negative x. Sorry about that. That's because you see what we actually just computed is twice the derivative. I don't want twice the derivative. I actually want just the derivative. All right. So let's go ahead and now take this second derivative, or in other words, the derivative of this picture right here. That's a product rule, so not too bad. The derivative of the first group is going to be just a negative b, because the derivative of a and b, those are constants, so those go away. So it's just negative bx that I'm concerned about. Derivative of negative bx, it's just negative b, times the second function, plus the first function times the derivative of the second function. Derivative of the second function is, well, derivative of e to the power is e to the power. And then you have to hop into the power and take its derivative. There you go. By the way, that should show you that had we started this whole problem by just factoring out e to the negative x, it would have been better. When you factor beforehand to get a nice product rule, sometimes it's a little cleaner. That's not that big of a deal though. This is going to equal negative b e to the negative x minus this, maybe I'll distribute it through. I'll say plus a e to the negative x minus b e to the negative x, and then plus bx e to the negative x. All right. Now what I'm going to do is I'm going to add y and 2y prime. Let me highlight that. Y. I want a different highlighter. Y and 2y prime and y double prime. I'm going to add them up. And when I do that, I'm going to collect like terms. That's what we've done all along with differential equations. So I'm going to add them up and say y double prime plus 2y prime plus y is equal to. It's equal to something times e to the negative x plus something else times x e to the negative x. Let's see what the something times e to the x is. E to the negative x, that is. I'll use yellow, the yellow highlighter, to highlight all the stuff that's attached to e to the negative x. Let's see. We have a from this guy. And actually, here's where distribution really helps out here. So I'm going to rewrite this as negative 2a plus 2b e to the negative x minus 2bx e to the negative x. Okay, so the stuff there that's attached to e to the negative x only is that. And then all this stuff right here is just attached to e to the negative x. So I'll go ahead and write all that stuff down. I'll use green for that. So we have a, let's see, minus 2a plus 2b, and minus b, and plus a, and minus b. That's the stuff attached to e to negative x. Now in a different highlighter, blue, I'll highlight the stuff that's attached to x e to the negative x. That would be a positive b, Let's see, what else do we have? For 2y double prime, it's a negative 2b. And finally, for the y double prime, we have a positive b. So let's go ahead and do that. And as I started kind of looking at this, I got a little nervous, but I'll show you why I'm not anymore, because I read the directions of the problem. So we have a b minus 2b plus b. And when I saw that, I thought, oh my gosh, that disappears. That's a problem. But it actually is not a problem, because the actual instructions were show that the function y equals a e to the negative x plus bx e to the negative x satisfies the differential equation. In other words, it doesn't actually matter what a and b are. It will always turn out, when you plug in that function, it'll turn out to be 0. Well, let's find out. This is equal to, let's see, I have a plus a minus 2a, those are gone. I have 2b's minus 2 more b's, those are gone. So 0 e to the negative x. And I have 2 of these b's minus 2 of those b's, so plus 0x e to the negative x. That is 0. Check. So we have shown that that given equation, y equals a e to the negative x plus bx e to the negative x, always satisfies this differential equation. It always makes this equation true. I was a little nervous because I was expecting to find an actual value for a and b, but rereading the instructions, I immediately realized, oh, no. They're just saying it should always be true, and it is. Very nice. It's a good problem. Now, this problem is very commonly assigned. And so what I'm going to do is actually just motivate it. I'm not going to finish it out. I'm just going to motivate the problem, because if it is assigned, I don't want to give you the answer. I would rather kind of nudge you along the direction or the path to the answer. In a previous section's homework for my students, they've already proven that the derivative of an even function is an odd function, and the derivative of an odd function is an even function. Now in this section, because you get to use the chain rule, they're asking you to reprove that, but only use the chain rule. Well, if we let f be an even function, so let f be even, we know one thing about that. That will imply that f of negative x is equal to f of x. We want to show that f prime of negative x is negative f prime of x. In other words, we want to show the derivative is actually an odd function. Okay, we possibly can do that. Here's my hint. Take the derivative of this, not both sides. Just take the derivative of this left-hand side. And then use the chain rule. I promise everything will work out. There is a little subtlety in it. Just going to give you a hint. There's a little subtlety. After you use the chain rule, you'll find out it's not exactly what you wanted to show. It's very, very close. Use the fact that f is even. You have to use that at some point. They told you that. They told you it was even. So you have to use that fact. So you're going to use the fact that f is even somewhere in your final product here. I can't tell you where without spoiling it, but you will have an f of negative x somewhere, oh, I don't know where, that you could trade out for an f of x. I'll let you figure out where that is. But in the meantime, the final example in the synthesis questions is this one. I used to assign this every semester because I love this problem. Suppose that y equals f of x is a curve that always lies above the x-axis. That is, it's always positive, so y is always greater than 0. And never has a horizontal tangent. Well, what does that mean? Y prime is not equal to 0. For any x, it's just never 0. Okay. Where f is differentiable everywhere. Okay, or y prime. Y is differentiable everywhere, that's fine as well. For what value of y is the rate of change of y to the fifth with respect to x 80 times the rate of change of y with respect to x? So now I've written down kind of the basic ideas. I can then go in and highlight the actual meat of the question. For what value of y is the rate of change of y to the fifth with respect to x? Okay, let me write that down. The rate of change of y to the fifth with respect to x. When is that 80 times the rate of change of y with respect to x? That is, when does that equal 80 times the rate of change of y with respect to x? Okay. Well, let's go ahead and figure this out. The derivative with respect to x of y to the fifth, again, we want to know when that's equal to 80 times the derivative with respect to x of y. Well, the derivative of y to the fifth by the chain rule. This is just a variable. Derivatives of variables to powers. You would reduce the power by 1 and bring that power out front. So this would be 5y to the fourth. That's the derivative of something to the fifth. It's 5y to the fourth. But then you have to take the derivative of what you just raised to the fifth, which would be y. And you want to know, when is that equal to 80 times, again, the derivative of y with respect to x? Okay. If you notice, they told you, that was critical, that y prime is never 0. That is, dy dx is a non-zero number. So you can divide both sides by dy dx and not worry. So I'm going to go ahead and divide both sides by dy dx. That's the critical part. If dy dx could be 0, there's no way I should be dividing by that. And now I'll divide both sides by 5. And I think that should be 16, I guess. And then I'll take the fourth root. Now, technically, you should get a plus or minus 2, because negative 2 to the fourth is 16 and positive 2 to the fourth is 16. However, they did tell us y is always positive. So I don't have to worry about the negative. And there is my function. For what value, not my function, but my y value. For what value of y is the rate of change of y to the fifth with respect to x 80 times the rate of change of y with respect to x? And that's a pretty cool example. Plus it previews where we're going. I did a little trick here. The derivative of some variable to a fifth power. Again, derivative of some variable to the fifth power is just the fifth power times that variable to the fourth power. Then you have to take the derivative of that remaining variable. You've actually been doing that with your polynomials for quite some time, believe it or not. If I asked you what's the derivative with respect to x of x to the fifth, it technically is actually 5 times that variable to the fourth times, let me go ahead and put this in red here, times the derivative of that variable with respect to x. It's actually the chain rule, but we just never write it that way. But derivative of x with respect to x is 1, or in other words, dx over dx is 1. So this turns into 5x to the fourth times 1, or 5x to the fourth. Nobody ever writes it that way, but it is true that the derivative of x to the fifth is 5x to the fourth dx dx. But again, dx dx is just 1. Anyhow, it's a little aside, but really fun problem. I dig it. So that's it. We are done with the chain rule material.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.